Hey everyone, this is Dr. Walker. This is video 256, magnetic field of a current loop. We just learned in the previous video that a straight wire produces a magnetic field around it. So you can imagine that if you have a loop of wire, well, that's also going to produce a magnetic field. It turns out that having the wire into a loop actually strengthens the field. And this is because all of the fields will add up. So if you look at this loop here, you can just think of it as being made of a bunch of straight segments of wire and think about which way is the magnetic field going due to each of these segments. For instance, if you had a segment of wire to the right, it would produce a magnetic field upward at the center of the loop because we would use the right hand rule number 2 and we would have our thumb to the right and our fingers are looping this way. And so if you are behind the wire up here, you're going up because we're looping this way. So you stop here and then you keep going and you can see it was going up. If you do the same thing for a segment of wire which is over here going into the page, then you put your thumb into the page like this and now you can see that your fingers are looping clockwise from your point of view. So if you are to the left, then you're also going up, right? Because you're going like this, going up. So no matter which segment of the loop that you're looking at, the magnetic field will always be up at this location, which happens to be in the center of the loop. So all of the magnetic fields add up and you have a stronger field than you would with just a straight wire. The equation for the field at the center of a coil with n turns is given by n mu naught I over 2r, where n is a number of turns or number of loops, mu is the permeability of free space, I is the current, and then r is the radius of the loop. Notice that we use a big R because the radius of the loop, r, is constant. So this formula can only give us the field at the center of the loop. It does not give us the field at a certain other distance from that loop. So this is just going to be a plug and chug equation, so we can go ahead and do the example right here in this video. It says a circular current loop of 10 turns carries a current of 5 amps. If the radius of the loop is 5 centimeters, find the magnetic field at the center of the loop. So for a loop, we have B equals N mu O I over 2R. And then we just plug and chug. So N is the number of turns, that's 10. Mu is the permeability of free space, that's 4 pi times 10 to negative 7. And then I is the current, which is over here. It's given as 5 amps. And then 2R, and then R is the radius. So that is 5 centimeters, but we convert it to meters. So R is 0.05 meters. So 0.05. And then we plug in all of these numbers, and we're going to get 6.28 times 10 to the negative 4 teslas. So that's the field produced at the center of the loop.